Welcome back. In this video, we are going to design a beam to be able to handle shear, and then if we have time in this video, we will also do deflection. So at this point, we've chosen a member that we know can handle the moment or the bending. Now we're going to use that member's properties to check to see if it can handle shear and deflection. So again, we know what member we chose in the last test where we did the bending moment, and now we're going to check its shear. So similar to the moment equation, you take your maximum shear and multiply it by a factor of safety. However, this factor of safety is different than the factor of safety used for bending. Here, the factor of safety is 1.5. So you take your maximum shear, whether it be from a moment and shear diagram or from the equations, you take the max shear and multiply it by 1.5, and then that is our design shear that we're using. So once you know what the design shear is actually applying to your beam, you will then check to see the strength of the beam. The strength of the beam is determined from this equation right here. This Vn is the strength of the member that you chose, and it is 0.6 multiplied by F of y, which is the yield stress, multiplied by A of W. Now, A of W is the area of the web. The web is this middle part right here, and then the top parts are the flange. So why is it the area of the web? Well, if you think about it, if you were to load this beam, and you were to keep loading it and loading it and loading it until it eventually failed from shear, a shear failure is when you just put so much weight on top of a member that the member just snaps. It does not bend and break. Bending and breaking would be bending moment failure. Shear failure is when there's just so much force pushing straight down that the member just snaps. So the member is not going to snap at the top part right here. It's going to snap where in the middle where the load's actually being traversed through. So this right here, the unhighlighted portions, they're not actually supporting the load of a shear. They are there for helping with bending by creating larger inertia. So when we're analyzing what it can handle regarding shear, we're only concerned with the portion that's going to be traversing the shear load, which is the web right down the middle. So how do I know what the area of the web is? Well, it's actually not going to be given to you straight up using the chart. You're going to have to calculate it. It's not that hard though, because you'll be able to find out what the depth is and what we say the thickness of the web, or T of W. Now those are what you're getting from the chart. So remember, we already figured out which member we're going to be analyzing. We did that in step 1. We're in step 2 now. Step 1, when we sized the beam. So say we chose a W 14 by 82, for example. If we chose a 14 by 82, the depth is 14.31, that's D, and then the thickness of the web is 0.51. Multiply those together, that's your area of the web. So take your area of the web, now we have inches squared, multiplied by F of y, which is going to be measured in PSI. Notice how pounds per square inch times square inch, well, they will cancel out, right? This inches squared. And what you're left with is kips. Shear is a kip force or pound force. And that's how you would determine what the actual strength is of the member. And once you have the strength of the member, you're going to compare that to what you calculated over here to make sure that your strength is greater than what is being applied. And if it is, yay. If not, you have to redesign. What does redesigning mean? Well, you have to choose a different member. Now, think for a second just logically. Imagine a beam. Close your eyes and imagine a beam. And the beam is loaded. And as the beam is loaded, it's going to bend, right? What do you think is going to fail first? The beam bending so much and then it becomes unstable? Or the beam not bending so much, but just so much loading on top of it that it just snaps in half? Think about it for a second. Is it going to fail first from bending too much and then becoming unstable, or too much load that the metal just snaps in half? If you guessed that it'll fail first from bending too much, you're correct. And that is exactly why step 1 was checking for bending moment. We check this first because this is typically how it fails first. And if it fails from bending first, usually if it can handle bending, it can handle shear. That's why we size the member based on bending, and then we check based on shear. So now we know how to check for shear. Let's recap and do the steps again. Step 1, find the maximum shear. Multiply it by the factor of safety, which is 1.5. It was 1.67 for bending. This value right here, V of n, is the nominal or the actual shear stress we designed the beam to be able to handle. And then we put that number on hold for a second. And then next, we're going to figure out what the strength of our members is, and then we're going to compare the two VNs. So using the beam that we chose to analyze from moment, we will multiply the area of the web, or the thickness, we're going to use the area of the web by multiplying the depth by the thickness of the web to give us the area. We're going to multiply that area by 0.6 multiplied by F of Y, which is the strength of steel or the yield stress of steel. And then that will give us the true shear strength of the beam. Now that we know the true shear strength of the beam, in step 4, we are going to compare that to the stress applied in step 2. And you have to make sure that your value in step 4, which is the strength of it, is greater than the applied stress over here. And if it is, we're good. Honestly, guys, a beam will almost never fail from shear loading. If it can handle a bending moment, it can most likely handle a shear force. The only time that you might ever see a beam fail from shear is if it's a really, really, really short beam and it won't really bend too much and it can handle a lot of loading, and then the shear will actually make it fail first. But that's only if you're talking a very, very short, small member. Okay, so that's shear. Let's do deflection now. All beams deflect, even from the smallest applied load. Even you walking across a steel beam will make it deflect ever so slightly. And although this isn't a true type of failure, we must check to see how much a beam will deflect. If a beam deflects too much, it will cause functionality problems with the building. Why? Well, think about it for a second. What would happen if the beam supporting a floor was bending too much? Well, the floor would bend too much. And why could that be a problem if a floor or a ceiling or a roof is bending too much? Well, several. It could cause cracks. If you have like a plaster or something that can crack, bending of a floor or a roof or a ceiling will make there be these ugly cracks in it. If there's a flat roof and now there's a little bowing going on, you'll have ponding. It could totally like trip you up if there's a sag in the middle of your floor and the room is now like kind of distorted. And just a designer's judgment. You know, if you have an uneven floor, your doors won't close properly. Things like windows will be distorted. If you drop a ball, it'll roll to the center. It's just bad for functionality. So we have to design a beam to only deflect so much. So how much is a beam able to be deflected? Well, we have an equation for what is considered an allowable deflection. So we say that the length divided by 240 is the allowable deflection for dead and live loads being applied. You know what dead and live loads are. Dead is like the weight of the structure itself, and live are things that move. So you take the length of the beam, divided by 240, and that's the allowable deflection. Not the actual deflection, the allowable deflection. The second equation is L over 360 for just live load. So you have to do this twice. once for the allowable deflection for dead and live, that's L over 240, and then L over 360 is the allowable deflection from just live load. And just a note, L must be in inches. Typically, L is going to be given in feet, multiply it by 12, and then that's what you'll be using. Okay, so now we know what the allowable deflection is. How do we know what the actual deflection is? There's various equations based on how it's loaded. Here's an example. Remember when I gave you like the beam shortcuts, and then it gave you the reactionary forces and the max moment and the max shear? Remember this over here? This is where it gives you the maximum deflection. And in this one, for example, when there's a member loaded right in the middle, point force right in the middle, the max deflection is P multiplied by L cubed divided by 48 EI. Well, I know what P and I know what L is, but what does 48 EI mean? E is the modulus of elasticity on the member. For a steel, which we're typically going to be working with, it's 29,000 KSI or 29 million PSI. You're probably going to be working in PSI because I is inertia. Remember we did inertia before? It's like the resistance to change of an object. So you can imagine an object with a larger inertia would deflect less. And inertia is measured in inches to the fourth, which is why you have to make sure that both L is measured in inches and E is in PSI, just to keep it apples to apples. So what is P? Well, P is going to be broken up into dead and live. So when you're doing the L over 240, the total P you use is the dead load and the live load. However, when you're doing the second one, you're only going to be using the live load portion of the total load. And I'll tell you like there's a 10 kip load total being applied, 4 kips are dead, 6 kips are live. And then you'll know that when you're doing the first one, you'll use the full 10. When you're doing the second one, you'll just use the live portion of it. And I will always give you these equations for deflection, no need to memorize. And so let's recap. You determine the allowable beam deflection by dividing the beam length by probably both 240 and 360, depending on the use. Using the beam shortcut equations provided, determine the actual beam deflection that will occur. So you get allowable deflection in step 1, you determine the actual deflection in step 2, and you ensure that the actual deflection is less than what's allowed. Disclaimer, beams will often have too much deflection, meaning the actual is greater than the allowed. This will happen a lot. And if this happens, you're going to have to pick a larger steel beam and then check deflection again. However, you do not need to check moment and shear again. If the moment and shear was good for a smaller beam, it's still going to be good for a larger beam. You're just checking the new deflection. And that's it for this video. In the next video, we're going to go through the entire process in a what I would consider comprehensive example.